For decades, aircraft designers faced a recurring problem. Wings that generated sufficient lift often suffered from poor low-speed behavior, difficult handling, or structural inefficiencies. Engineers experimented with different shapes, reinforced structures, and increased engine power, yet stalls remained unpredictable and performance gains were limited. In many cases, aircraft were controllable only within narrow speed ranges, making training and operation risky. The underlying issue was not the aircraft as a system, but the wing profile itself. Virginius Clark identified a simple airfoil geometry that provided reliable lift, stable handling, and practical manufacturability. Once introduced, this airfoil was adopted across thousands of aircraft designs and became one of the most widely used wing profiles in aviation history. Virginius Everett Clark Jr. was born in 1886 in the United States, at a time when powered flight did not yet exist as an engineering discipline. Aviation was still experimental, and aerodynamics was largely theoretical, rooted in fluid mechanics rather than applied aircraft design. There is no evidence that Clark came from a family of aviators or engineers involved in early flight. His path into aeronautics was shaped not by family tradition, but by formal education and emerging institutional research structures in the early 20th century. Clark pursued engineering studies during a period when American universities were beginning to formalize aeronautical engineering as a distinct field. He studied mechanical and aeronautical engineering, with advanced training that emphasized applied mathematics, structural mechanics, and fluid behavior. His education coincided with the transition from experimental aviation toward scientifically grounded design. This background would strongly influence how he approached aerodynamic problems later in his career. After completing his university education, Clark entered professional engineering at a critical moment. World War I had accelerated aircraft development, but much of that progress had been achieved through trial and error rather than predictive design. Aircraft wings were still being shaped largely by empirical modification. Designers relied on camber changes, structural reinforcement, and engine power increases to improve performance, often without a clear understanding of why certain shapes worked better than others. In the early 1920s, Clark joined the National Advisory Committee for Aeronautics, NACA, the US government research organization established in 1915 to provide scientific foundations for aviation. NACA's mission was not to build aircraft, but to understand the physics governing lift, drag, stability, and control. This environment suited Clark's analytical approach. Unlike aircraft, manufacturers constrained by production deadlines, NACA engineers could focus on isolating fundamental aerodynamic problems. At NACA, Clark was assigned to aerodynamic research related to airfoil behavior. At the time, airfoil design was one of the most significant unresolved challenges in aviation. Existing airfoil shapes often delivered good lift at certain speeds, but exhibited sharp stall behavior, high drag, or manufacturing difficulty. Many airfoils performed well in wind tunnels, but behaved unpredictably in real flight conditions, especially at low speeds. Clark's early work focused on understanding how airfoil geometry affected lift coefficient, pitching moment, stall characteristics, and pressure distribution. Unlike earlier designers who prioritized maximum lift, Clark placed emphasis on predictability and controllability. He recognized that many aircraft accidents and handling problems were linked not to insufficient lift, but to unstable stall behavior and excessive sensitivity to angle of attack changes. Another issue Clark identified was manufacturability. Many existing airfoil shapes were aerodynamically efficient but difficult to produce consistently with early 1920s manufacturing techniques. Thin trailing edges, complex curvature, and sensitivity to surface imperfections made large-scale production unreliable. Clark understood that an airfoil's value depended not only on theoretical performance, but on whether it could be built accurately and maintained in service. This combination of concerns, lift, stability, and manufacturability defined Clark's research direction. Rather than seeking an airfoil that maximised performance in one narrow regime, he aimed to develop a balanced airfoil that delivered adequate lift, gentle stall behaviour, and consistent performance across a wide range of speeds. By 1922, Clark's work led to the development of what would later be known as the Clark Y airfoil. This airfoil was characterised by a flat, lower surface over much of the chord, moderate camber, and a thickness distribution that allowed predictable airflow behaviour. The flat lower surface simplified construction and alignment, while the overall geometry produced stable lift characteristics and reduced pitching moment variability. Importantly, Clark did not initially design the Clark Y to become a universal solution. It was developed as part of NACA's systematic airfoil testing program, documented in NACA technical reports, where airfoils were evaluated under controlled conditions and compared using consistent metrics. The Clark Y distinguished itself not by extreme values, but by reliability and repeatability. Early test data showed that the airfoil produced sufficient lift at low speeds, stalled gradually rather than abruptly, and maintained acceptable drag characteristics for training and general-purpose aircraft. These qualities made it attractive to designers who needed aircraft that were forgiving, stable, and easy to operate, especially as aviation expanded beyond test pilots to civilian and military training environments. Clark's role at NACA positioned him as a bridge between theoretical aerodynamics and practical aircraft design. He did not frame his work in abstract mathematical terms alone. He framed it as an engineering solution to operational problems. This mindset would later explain why the Clark Y airfoil spread so rapidly across different aircraft categories. By the mid-1920s, Clark had established himself as a key contributor to American aerodynamic research. His work reflected a broader shift in aviation, away from chasing peak performance numbers and toward designing systems that balanced performance, safety, and manufacturability. This foundation, education grounded in engineering physics, early exposure to systemic aerodynamic problems, and work within NACA's research culture set the stage for Clark's lasting impact on wing design. What followed was not a single aircraft or program, but the widespread adoption of an airfoil that quietly reshaped how wings were built and flown. By the mid-1920s, aviation faced a design contradiction that engineers could no longer ignore. Aircraft needed to carry heavier loads, fly longer distances, and remain controllable at low speeds, especially during takeoff and landing. Yet improving lift usually came at the cost of increased drag or poor handling. Existing airfoils were either efficient at higher speeds, but unstable at low speeds, or stable at low speeds, but inefficient overall. This trade-off limited aircraft performance across both military and civil applications. At the National Advisory Committee for Aeronautics, NACA, Virginius Clark focused on resolving this contradiction through systematic airfoil research rather than incremental modification. Instead of pursuing radical shapes, Clark studied how pressure distribution and camber influenced lift, drag, and pitching moment under realistic operating conditions. His objective was not to maximize peak performance in ideal conditions, but to produce an airfoil that behaved predictably across a wide range of speeds and angles of attack. The key challenge was low speed lift with controllability. Many early airfoils generated sufficient lift, but did so with unstable pitching characteristics. Pilots experienced abrupt stall behavior, strong nose-down moments, or excessive control forces. These characteristics were unacceptable for training aircraft, transports, and military platforms operating from short or unprepared runways. Clark approached the problem by rethinking airfoil camber and pressure recovery rather than thickness alone. Through wind tunnel testing at NACA Langley, he evaluated multiple airfoil profiles under controlled conditions, measuring lift coefficients, drag coefficients, and moment characteristics across varying Reynolds numbers. His focus was consistency rather than extremes. The result of this work was the Clark Y airfoil. Introduced in 1922, the Clark Y featured moderate camber, a relatively thick profile for structural strength, and, most importantly, a flat lower surface from approximately 30% of the chord to the trailing edge. This flat bottom geometry was not a cosmetic choice. It simplified manufacturing and alignment while providing predictable aerodynamic behavior. Aerodynamically, the Clark Y delivered several advantages simultaneously. It produced high lift coefficients at low angles of attack, allowing aircraft to take off and land at lower speeds. Stall behavior was gradual rather than abrupt, improving safety and controllability. The pitching moment was moderate and stable, reducing trim changes across speed regimes. Drag levels remained acceptable across cruise conditions, even if the airfoil was not optimized for high-speed flight. This balance made the Clark Y uniquely versatile. Unlike specialized airfoils designed for narrow performance windows, the Clark Y performed reliably across multiple mission profiles. This made it especially attractive for aircraft designers who prioritized operational safety, structural simplicity, and predictable handling over marginal performance gains. Manufacturing considerations further increased its appeal. The flat lower surface allowed wings to be built with simpler jigs and fewer precision requirements compared to fully curved airfoils. This reduced production time and cost, critical factors during the rapid expansion of aviation in the 1920s and 1930s. As a result, the Clark Y was adopted widely and rapidly. It became one of the most commonly used airfoils of the interwar period, appearing on training aircraft, light transports, reconnaissance planes, and early military aircraft. Designers trusted it because its behavior was well documented and repeatable. NACA test data provided clear performance envelopes, allowing engineers to design wings with fewer unknowns. Importantly, the Clark Y did not represent a theoretical maximum in aerodynamic efficiency. Clark did not claim it minimized drag or maximized lift-to-drag ratio under all conditions. Its importance lay elsewhere. It established a practical standard for airfoil behavior that balanced aerodynamic performance with real-world constraints. This distinction mattered. Aircraft design during this period was shifting from experimental craft to operational systems. Reliability, predictability, and ease of production mattered as much as raw performance. The Clark Y met these requirements better than most alternatives available at the time. Clark's work also influenced how airfoils were evaluated. Instead of focusing on single performance metrics, engineers began assessing airfoils as integrated contributors to aircraft behavior. Lift, drag, pitching moment, and manufacturability were treated as interconnected variables rather than isolated targets. This systems-oriented approach aligned closely with NACA's broader mission. The Clark Y was not just an airfoil, it was a demonstration that disciplined testing and balanced design could produce solutions that scaled across an entire industry. By the late 1920s, the Clark Y had become a reference point. Even when designers chose different airfoils, they compared them against Clark Y data. It served as a baseline for evaluating improvements, not because it was perfect, but because it was well understood. Virginius Clark did not attempt to revolutionize aviation with complexity. He reduced uncertainty. Through careful testing, conservative geometry, and clear documentation, he provided designers with a tool they could trust. In an era where many aircraft failed due to unpredictable behavior, that trust was decisive. The Clark Y airfoil did not push aircraft to new speed records. It allowed aviation to grow safely, reliably, and at scale. That contribution shaped an entire generation of aircraft and set the stage for the more specialized aerodynamic advances that would follow. By the late 1920s and early 1930s, the Clark Y airfoil had moved beyond experimental validation and entered widespread industrial use. Its adoption was not driven by marketing or institutional pressure, but by practical results. Aircraft manufacturers found that designs using the Clark Y consistently met performance targets, with fewer surprises during testing. Lift characteristics were predictable, stall behavior was manageable, and manufacturing tolerances were forgiving compared to more aggressive airfoil shapes. This reliability made the Clark Y especially attractive during a period when aircraft production was transitioning from small batches to standardized manufacturing. As aviation expanded into commercial transport, training aircraft, and military procurement, consistency became as valuable as raw performance. Designers needed airfoils that worked across a wide range of weights, speeds, and operating conditions. The Clark Y provided that margin. During the 1930s, the airfoil appeared on numerous American aircraft, including trainers, light transports, and early military designs. It was particularly well suited to aircraft that operated frequently at low to moderate speeds, where controllability and safety were critical. Training aircraft benefited from gentle stall characteristics and stable handling, reducing accident rates and simplifying pilot instruction. Transport aircraft benefited from efficient lift generation at practical cruise speeds without requiring complex wing structures. As World War II approached, the priorities of aircraft design shifted rapidly. Production speed, reliability, and maintainability became dominant concerns. Aircraft had to be built quickly, flown by pilots with limited training time, and maintained in austere environments. The Clark Y aligned naturally with these constraints. Its flat lower surface simplified wing construction, reducing tooling complexity and assembly time. Its predictable aerodynamic behavior reduced the need for extensive flight test revisions. Although more advanced airfoils were developed during the war for high-speed fighters and specialized roles, the Clark Y remained in widespread use for aircraft, where extreme performance was not the primary objective. Many training aircraft, liaison planes, and utility transports continued to rely on Clark Y-based wing designs throughout the war. In these roles, reliability mattered more than marginal gains in speed. Importantly, the Clark Y also influenced aircraft that did not use it directly. Designers used it as a baseline reference. New airfoils were often evaluated by comparing their performance, stall behavior, and manufacturability against the Clark Y. If a new design did not offer clear advantages without introducing new risks, it was often rejected. In this way, Clark's work shaped design decisions even when it was not visible in the final product. After World War II, aviation entered a period of rapid technological change. Jet propulsion, swept wings, and transonic aerodynamics transformed aircraft design. In this new environment, the Clark Y was no longer suitable for frontline high-speed aircraft. However, its influence did not disappear. General aviation expanded dramatically, and many post-war light aircraft adopted airfoils derived from or inspired by Clark's principles: moderate camber, predictable lift curves, and stable stall behavior. Flight schools, private aircraft owners, and small manufacturers valued these characteristics. Safety, ease of control, and low operating costs mattered more than absolute performance. The Clark Y became embedded in the DNA of general aviation, shaping how small aircraft flew and how pilots learned to fly. From an engineering perspective, Clark's most lasting contribution was not a specific shape, but a design philosophy. He demonstrated that an airfoil could be optimized for real-world operation rather than theoretical extremes. By balancing lift, drag, stability, and manufacturability, he showed that engineering success often comes from restraint rather than ambition. This approach influenced how NACA and later NASA evaluated aerodynamic solutions. Designs were judged not only by peak performance, but by behavior across operating envelopes, sensitivity to surface imperfections, and compatibility with production realities. Clark's work reinforced the idea that aerodynamic theory must serve operational needs, not just mathematical elegance. Virginius Clark did not seek recognition as a visionary. He did not attach his name to bold predictions or revolutionary aircraft. His impact was quieter. He provided a tool that worked and kept working across decades of technological change. Engineers trusted it, pilots relied on it, manufacturers built around it. Today, the Clark Y airfoil is still studied in aeronautical engineering programs. It is used to teach fundamental concepts of lift, camber, stall behavior, and design compromise. Students encounter it not as a historical curiosity, but as a practical reference point, a reminder that effective engineering often prioritizes clarity and control over novelty. Clark's legacy is visible in thousands of aircraft that flew safely because their wings behaved as expected. It is present in the culture of American aviation engineering, where predictability and system-level thinking are valued as much as performance. He did not redefine what wings could do at the extremes. He defined how wings should behave where flight actually happens, and that is why his work endured.